In this section, we discuss metal semiconductor junctions, which are important for making semiconductor devices. Depending on the alignment of the metal Fermi level with the semiconductor bands, one can get a diode-like non-ohmic contact, which can be used to make a diode. Or it may be undesirable as it will add additional losses to the circuit. Ohmic contacts can usually be achieved by choosing a different metal or engineering the interface for better band alignment. Imagine we are trying to make a metal semiconductor junction. Now we have two different materials, one with a band gap and one without. Again, electrons will move from the material with higher Fermi level to the one with lower Fermi level, in this case from the semiconductor to the metal. Like the p-n junction, this will lead to a depletion region, internal electric field, and band bending. The bands will bend to make the Fermi level constant throughout. This means that the electric potential will be produced that raises the left side and lowers the right side. As we saw in the p-n junction, the n-type material here will be depleted of electrons and become positively charged in the space charge layer. The metal will gain electrons located at the interface, which we can think of as an extremely thin space charge layer. Recall that the thickness of the space charge layer depends on the doping level, with thinner space charge layers for higher doping. So the metal with an extremely high charge carrier concentration acts like it has an infinitesimally thin space charge layer. Thus, the electric field is only in the semiconductor region, so the band bending only occurs in the semiconductor region. Notice that far away from the junction, the Fermi level is in the same location relative to the bands as before contact. It is only the vacuum level that has shifted. The built-in potential and extent of band bending is simply the difference in Fermi level before contact, which is the same as the difference in work function. The offset between the metal level and the bottom of the conduction band, or the top of the valence band, is the same as it was before the creation of the built-in potential and band bending. This offset between the metal Fermi level and the bottom of the conduction band, phi b, acts like a barrier for electrons trying to go from the metal into the semiconductor and is called the Schottky barrier. Notice the Schottky barrier to the conduction or valence band depends on where the metal Fermi level is relative to the semiconductor bands. Experimentally, the Schottky barrier is often very different than that expected from this equation based on the work functions, and depends on the materials processing. This is because of charge defect states at the interface and is called Fermi level pinning. This metal semiconductor junction has an IV characteristic of a diode and is called a Schottky diode. In forward bias, the electrons in the conduction band of the semiconductor have to go over the barrier caused by the built-in voltage to get to the metal. Because most of this applied bias voltage drop will be across the space charge layer where there are few charge carriers, under forward bias the built-in voltage is reduced. The electrons in the conduction band of the semiconductor can readily overcome the small potential barrier, fall off the cliff due to the band offset, to enter the metal. As the barrier is reduced by bias voltage, the current rises exponentially. Under reverse bias, the electrons must move from the metal to the semiconductor. In this direction, the barrier is due to the band offset at the junction, as opposed to the built-in voltage, and so the barrier is not reduced in reverse bias. Thus, electrons in the metal cannot easily overcome the potential energy barrier phi b to enter the semiconductor. The small reverse bias current is nearly constant as given by the diode equation. Since this reverse bias current is essentially due to the thermal excitation of electrons in a metal that are able to go over a barrier, the current should be similar to that for thermionic emission, which is given by the Richardson equation. As expected, this includes an exponential of the band offset barrier over kT. P-type semiconductors also make Schottky junctions when there is a similar band offset with the valence band due to the Fermi level of the metal being higher than the valence band edge. While Schottky junctions can be used as diode devices, they are not great for simply contacting a semiconductor. They either limit the current or reduce the voltage, leading to a nonlinear IV characteristic very different from a normal resistor and are often called non-ohmic contacts. For an ohmic metal semiconductor contact, we want to avoid making a Schottky junction. We can do this for an N-type semiconductor by having the Fermi level of the metal above that of the conduction band edge in the semiconductor. In this case, the electrons from the metal move into the semiconductor to raise the potential and equilibrate the Fermi level. At the junction, the Fermi level is actually above the conduction band edge, making the semiconductor degenerately doped like a metal. Electrons can then cross the junction in either direction without any energy barrier, making it ohmic and having less resistivity than the bulk semiconductor. P-type semiconductors also work similarly, where metals with low Fermi level, high work function, below the valence band edge should make ohmic P-type contacts. In practice, charged interfacial defect states may pin the metal's Fermi level somewhere else, making it challenging to create ohmic contacts without changing processing conditions that affect the interface structure, chemistry, and impurities.